Moving on to section 6.1, we have continuous probability distributions, and more of a focus on it. So here's an example. The emissions of a particulate matter, a form of pollution consisting of tiny particles for 65 vehicles in units of grams of particles per gallon of fuel are shown below. Well, how reverting back to chapter 1 material using histograms, so we can divide the data in bins and classes, and the bins, obviously we know, are intervals of equal width that cover all the values that are observed. And then we can choose the bins to be from 0 to 1, 1 to 2, or we can make it 0 to 0.5, 0.5 to 1. It just matters, there's a good moderation between too narrow and too wide. And we count the number of observations that fall into each bin to obtain the frequencies. So an example of this is, so we use bin interval widths of 1, so we created the histogram down here, and here's our summary table, is what I want to call it, and you can count. The histogram has relative frequency, but we can also tell the frequency from this by multiplying the probability. So 0.4 times the total number of observations will give you 26, and so on. So that's an example of a continuous PDF. Now, if we had information on an entire population containing millions of vehicles, we could make the rectangles extremely narrow because we have millions of data points. So bin interval width won't really matter that much because it's going to be a large continuous distribution, like so. And the histogram would look smooth and could be approximated by a curve. And you see that here. And you also know that this is a skewed right distribution that tails off to the right. So let x be a continuous random variable. The PDF of x is a function of f of x, such that any two numbers a and b with a less than or equal to b. So here's point A and here's point B. This curve is a PDF, or the graph of f of x is this curve. And here's the 2 points, the area below it. So the probability of A less than or equal to x, less than or equal to b, the area under the density curve between A and B, and that's the probability. And that makes sense. So here's continuous data and probability, or PDFs. So this curve is the waiting time and the density of people. So you can see that if we wanted to figure out the waiting time from 0 all the way up to 2, we could find it under this curve right here, from point B, which is 2, and point A. And the area under the curve between two values represents the probability. We talked about that on the previous slide. The total area under this curve that I'm highlighting here has to be 1, and the curve cannot lie below the x-axis. You see it comes straight to the x-axis. And here's a different example. So what if we wanted to find the probabilities for a uniform distribution, which looks something like this? It looks like just a rectangle. So the bus that runs near the home of one of the authors arrives every 12 minutes. If the author arrives at the bus stop at a randomly chosen time, then the probability distribution for the number of minutes he must wait for is shown right here. So the curve above shows the PDF for the wait time that a bus comes every 12 minutes. And this entire curve equals 1. 12 times this number here equals 1. So what if you wanted to find the probability that you will wait between 5 and 10 minutes? So we know previously we could use shading under the curve. So that represents the probability of 5 less than x less than 10, and you can shade it in, and then finding the area of a rectangle, half the base times the height. So 10 minus 5, that's 5. Well, half of that is 2.5 times this probability right here. That's the height. So it's 2.5 times this number. So, and that just says it right here. So it's 0.41655. That's the probability that you wait between 5 and 10 minutes at the bus stop. So find the probability that you will wait exactly 5 minutes. Well, you can't exactly do that because you can't take the area of a line because the line has a width of 0, and so that's what the base would be here. And so you can see right there. Does probability of 5 less than or equal to x less than or equal to 10 equal the probability of 5 less than x less than 10 for a continuous distribution? The answer is, I'll let you guess, yes. Yes, it is. It's the same. So the region above has a single point with no width, thus no area. So therefore, if x is a continuous random variable, probability of x equals a equals 0 for any number for a continuous distribution. A reminder that we're talking about continuous distributions. So this means that probability of a less than x less than b is equal to probability of a less than or equal to x less than or equal to b for any numbers a and b. So finding areas under the curve. In general, finding areas under curves that are not geometric shapes like rectangles is difficult and requires some type of computer-based technology. And that will be it for continuous distributions. There wasn't too much there, but if you have any questions about the notation or kind of what I was talking about, I would appreciate your comments.